Hello, viewers. In today's class, we are going to discuss yet another important and very conceptual problem from integrals, right? So here in this lecture, we'll again solve a very nice integral, which is 0 to infinity, and we have dx over x cube plus 1, right? So this is a very important integral which appears in calculus of residues, and we can also solve this integral by the method of using the Cauchy's residue theorem. But in this series we are focusing on the application of beta and gamma functions, right? So we'll solve this integral by using the concept of beta and gamma functions, right? We'll also solve these all type of integrals using the calculus of residues in our next series, right? So let us take this integral as I, right? So again, we'll take help of the method of substitution. So here we'll make this substitution, that is let x cube is equal to t, right? So x can be written as t raised to 1 by 3. So differentiating both sides with respect to t, we have dx over dt is equal to 1 by 3 t raised to 1 by 3 minus 1. Using the power rule for differentiation, 1 by 3 t raised to minus 2 by 3, right? So dx can now be written as 1 by 3 t raised to minus this is 2 by 3, and here we have dt, right? Now see, the limits vary from 0 to infinity. So when x is 0, we can take the value of t from this relation. So t is also 0, and here when x tends to infinity, then t also goes to infinity, right? So now this integral I can be written in terms of t as 0 to infinity. For dx, we can write 1 by 3 t raised to minus 2 by 3 dt divided by x cube plus 1. X cube is t, so we have t plus 1, right? So let us rearrange the terms. So we have 1 over 3, 0 to infinity, t raised to minus 2 by 3, and here we can write 1 plus t, writing t plus 1 as 1 plus t raised to 1, right? So now we'll convert this integral into the beta function. So now see, we can rewrite this integral as 1 over 3, 0 to infinity. Now t raised to minus 2 by 3 can be written as 1 over 3 minus 1, right? So we have already explained this method in our earlier videos, how to write this exponent and this exponent, right? So we have t raised to minus 2 by 3 as 1 by 3 minus 1. Here we have dt, and 1 plus t raised to 1 can be written as 1 by 3 plus 2 by 3, right? So because 2 plus 1 3 over 3 is 1, so we'll get the same integral. So the purpose of writing this integral like this is the beta function, because beta function is responsible for writing this integral in this form, right? Because beta function is defined like this: 0 to infinity x raised to m minus 1, 1 plus x raised to m plus n dx, right? So the value of m is obviously 1 over 3, and the value of n is equal to 2 by 3, right? So now this integral is equal to 1 by 3 beta of 1 by 3 and 2 by 3, right? So let us make use of another important relation in beta gamma function, that is beta mn is equal to gamma of m, gamma of n divided by gamma of m plus n. So here we have 1 over 3, gamma of 1 over 3, gamma of 2 by 3, and then we have gamma of 1 by 3 plus 2 by 3, right? Now see, this term is 1 by 3 plus 2 by 3, that is equal to gamma of 1. Gamma of 1 is equal to 1. So this expression is now equal to 1 by 3. We have gamma of 1 by 3 and gamma of 2 by 3. So gamma of 2 by 3 can also be written as 1 minus 1 over 3, right? So the purpose of writing gamma 2 by 3 like this, gamma 1 minus 1 by 3, because this expression can be written like this, that is gamma of n, gamma of 1 minus n is equal to pi over sine n pi, right? So this is the famous Euler's reflection formula in beta gamma functions. So here n is 1 by 3, right? So here we have gamma 1 by 3, gamma 1 minus 1 by 3. So this expression is now pi over sine, that is pi over sine n pi. So n is 1 by 3. So here we have pi by 3. So now we have 1 over 3 pi. Sine pi by 3 is sine 60 degrees. That is a square root of 3 over 2, right? So now the value of this integral I can be written as 2 pi. This 2 goes to the numerator. So we have 2 pi over 3 root 3, right? So viewers, the value of this integral is equal to 2 pi divided by 3 times the square root of 3. So this is how, by the application of beta and gamma functions, we can solve these kind of integrals.